This is going to be a somewhat unusual video in which essentially I'm going to do one problem, and that's all that's going to happen in this video. The problem I'm going to do is one that I've often done in class. The reason I like to do it at this point is because it involves doing all of the things about stoichiometry that we've been talking about for the last several days now. It's got some solution chemistry, it's got some equation balancing, it's got something a bit like limiting reactants, and it's got all that wrapped around an actual application, something that is useful in the world. Okay. Having said all that, I will point out that there are one or two points along the course of this problem when I'm going to do something that I'll do my best to explain, but I'll also be acknowledging that I would not expect very many of you to make the same choice or decision that I'm going to make. Okay, there are some points in this problem where I have to do a couple things that require a certain amount of familiarity with how things work in solutions and whatnot. And so I don't want you to walk away feeling like this is a problem that I think you should be able to do in its entirety, but I do think it's a good way to sort of summarize a lot of the different concepts and ideas we've been talking about for a couple weeks now. So let's get to it. So my problem involves water treatment, all right? It involves specifically the removal of hydrogen phosphate ions from water, as might happen in a sewage treatment plant, okay? There's a photo over there of a water treatment facility from somewhere in the Dallas area that I slapped in there to point out that this is an actual thing that really happens, okay? Those hydrogen phosphate ions are things that phosphate ions of various sorts have often been used in different kinds of detergents. A lot of them have been regulated out of those products by now. Sort of over the course of my lifetime, I've watched them be removed from laundry detergents and dishwasher detergents and things like that. But they are still handy in some situations. They're good at cleaning things. That's why they used to be used in a lot of consumer detergents, okay? Nowadays, their use is mostly confined to commercial water treatment. Those ions are good for cleaning the water. They get rid of some things that it's important to get rid of, but then they're also not good to release out into the water stream. So in the confines of the water treatment plant, those ions would be used to treat the water, but then they need to get back out of the water before that water can be released out into the world. Okay, so that's kind of the way this would go, is those hydrogen phosphate ions might be introduced early on in the water treatment process, but then once they've done what they're there for, they need to be removed. They can be removed by treating the water with what is often referred to as lime, at least in this sort of industrial application. Lime is another term for calcium oxide, which has the formula just CaO as written there, okay? When that lime dissolves in water, it says it produces calcium ions and hydroxide ions. So something a little bit funny happens there, because we get hydroxide ions by dissolving something that doesn't appear to have any hydrogen in it. That's one of the places where we're going to have to do something a little tricky. The phosphate ions then precipitate, meaning they get converted into a solid, and that solid is the rather imposing looking formula there, which is referred to as hydroxyl apatite, is a name for that, that substance, okay? So far, my problem is relatively simple because it doesn't include any questions, but we'll fix that now. So the problem part of the problem involves this. So the question is, how many kilograms of lime would I need if I was at a step in the water treatment process where what I wanted to do was to remove all of the phosphorus from a 10,000 liter tank, which has that molarity there, 0.0156 molar concentration of hydrogen phosphate ions, okay? So I want to remove all of those phosphate ions, get them into the solid phase. That's going to be useful, right? Once they're in the precipitate, remember, precipitate is a solid substance that forms when we mix something in solution, right? Once it's a solid, then we can filter it to get that stuff out of the water, right? So the separation is easy once I have the ions in a solid rather than dissolved in the solution. Problem like that, as stated, would be very difficult indeed. So we're going to at least a little bit try to break it down into to pieces. The first thing we're going to do is we're going to generate two chemical equations. The first one of those is just for dissolving the lime in the water to figure out how we make the hydroxide ions by dissolving calcium oxide. The second one is a little bit trickier. That involves writing an equation for the precipitation reaction. Then the third step also has a little bit of a clever notion in it. That is, we're going to use those two equations to solve the problem, to actually figure out how much lime we would need to pull off this, this task, okay? So let's go ahead and get started. First one says, I'm dissolving the calcium oxide in water. I want calcium ions and hydroxide ions. So let's start by doing what I would normally do, which is to say, I know I have calcium oxide as a reactant, okay? On my product side, I know I want calcium ions and I want hydroxide ions because that's what it tells me. Okay. That's an equation right now that obviously there's no way we're going to pull off balancing that because I've got hydrogens on one side in the OH and I don't have any hydrogens at all on the other side, right? So to do this, this is going to be a situation where I'm actually going to have to write the water as part of the equation. That doesn't always happen, but if we just ask ourselves what's actually in this container, we know there's calcium oxide because we threw that in, right? But we threw it into something that is mostly water. Right, it's a lot of water with a little bit of the phosphates in there, perhaps. But that says to get hydrogen on this side, the one thing that I can definitely write there is water. And if I do that, then once I have the water in there, I can see that right now I have two hydrogens and two oxygens on the left, and I have only one of each of those on the right. That means I want to hang a 2 on the hydroxides. When I do that, notice that it also fixes up my charges, right? We said charges have to balance as well. And now I have 2 plus from the calcium ion, and I have 2 times -1 from the hydroxide ion. So I have 0 charge on the right, and I have 0 charge on the left. So that's my first balanced equation, okay? The one thing in there that was a little bit weird was the idea that I had to actually write the water in the equation. Okay, that does happen for things in there. You just have to keep in mind, okay, what else is in the container? In this instance, it's fairly obvious I need to get something on the left that has hydrogen in it, and water is the obvious thing that I should be using to do that. Does it matter if we use up some of the water? Not really, because there's just so many more water molecules in this tank than there are amounts of any of the other substances there that it's readily available. All right, that is the relatively simpler, I suppose, of the two equations, but it does introduce us to this idea that says we can just stick water into the equation for something that is reacting in an aqueous medium, meaning just in a bunch of water. Next up, I'm going to try to write an equation for the precipitation of the hydroxyl apatite there, okay? So let's see what's in the solution. In my solution, or in my holding tank, at this point, we know I have calcium ions. Okay, that's a 2 plus. I have hydroxide ions. I just got those by dissolving my lime, right? We know I have my hydrogen phosphate ions. That's the whole thing we're trying to get rid of. So that's in there. And the other thing that is in my tank, we just proved, is we also have plenty of water. Okay, so once again, if we need to, we're going to be able to add that water into our equation on one side or the other whenever that becomes a useful thing to do. Okay, and we are going to need to do that. I will just give you an early warning. All right. So let's see, we know we want this precipitate, the hydroxyl apatite over here. That's going to be the product, right? That's what I'm trying to produce. And so I know I want the calcium and the hydroxides and the hydrogen phosphates all need to be on the reactant side. So let's start by setting that up, because that's where the various things that are in my precipitate are coming from. I'll say that, I'll say OH minus, I'll say plus my hydrogen phosphates. And I will say on this side, I know I want the calcium, the hydroxyl apatite, the calcium containing precipitate. So the first thing I'm going to do here is I'm going to teach us a little trick that I don't think I've offered up before. That is, if I look at this equation, every place there's a P, it's part of a PO4, right? A phosphate group. So I'm going to balance PO4 as if that's an element, basically, and then I'm going to balance the other O's separately. Okay, you don't have to do that. We could do it without doing that, but it's going to balance a little bit more simply if I just make the PO4s the same on both sides. And the reason that's going to work, again, is just because every place there's a P, there's an O4 right after it. Okay, so that part will make things a little bit easier. I know, having done this problem before. I have 5 calciums over here. I have only 1 over here, so I'm going to hang a 5 there as a tentative coefficient for my calcium ion. Okay. If I look at the phosphates, I have 3 of those in here. I have them one at a time in here. So if I put a 3 there, I have 3 phosphates on both sides now. So those are okay. I have still an OH over here. I have an OH there, but then I have now 3 hydrogens here and nothing that I can balance them with. Okay, so I'm in a bit of a bind once again. All right. This is certainly the kind of advanced equation balancing, if that's a thing right now that we're about to do. I want to find a way to add I want to find a way to add 3 hydrogens to the right-hand side of my equation. Okay. I also have a problem right now with my charges because I've got plus 10 and minus 7 on the left. So I've got a plus 3 charge on the left, and I have no charge at all on the right. So something is messed up in the charge balancing as well. Okay. If I think about what I did in the first equation and what I wrote up there on the top of the screen, the way to get more hydrogens on the right-hand side is going to be to put the water over there as a product this time, okay? So I'm going to start by writing plus water over here. But notice when I did that, I didn't just add hydrogen. I added hydrogen, I added an oxygen. My oxygens were balanced before, so that's not so good, okay? The way to get this to work out and to be able to add 3 hydrogens to the right is to realize that if I put an OH minus on one side and I put an H2O on the other side, the net effect of that is going to be to add 1 H to the right-hand side, okay? Because you can think of H2O as being HOH, if you really want to. And that says, in addition to the OH, which I'm adding that to both sides, that doesn't mess up the balancing of anything. So each time I do that, I would add 1 hydrogen, okay? I want to add 3 hydrogens to the right-hand side. And so what I'm going to do is I'm going to add 3 OHs to the left, and I'm going to add 3 waters to the right. So that says this gets a 3. I'm adding 3 OHs, which means this one becomes a 4. When I did that, notice I also added 3 more negative charges to the left-hand side. So my charges now are going to work themselves out, I believe. I still have plus 10 from the calciums, right? This is 5 times 2, so this is plus 10. This is minus 4. This is minus 6, so those sum to 0. I have 0 charge on this side, okay? So this gives me a balanced equation. Like I said, this is definitely one of those places where I would not expect the majority of people in the course to just like have me say, okay, take this equation and balance it, right? It requires a lot of just familiarity with how these things can work, okay? If you do feel like you would have done that, then that's awesome. If you don't let it bother you, okay? I'm really just trying to get us sort of sorted through thinking about, we want to do a stoichiometry problem, we have to balance the equation. Now we've got the equations, right? So now we have a stoichiometry problem. It's still a little complicated, I will say. So this is the original problem statement, right? How many kilograms, how much lime do I need? That's the question, right? It's a stoichiometry problem because stuff is reacting and because it's asking how much do I need, how much lime, right? And then I have the thing I know is I know the volume and the molarity for my original phosphate ions, right? So that's going to be where I'm going to start the calculation. One of the things that's a little complicated right now is I have 2 equations, okay? The bottom equation is where these things here, the calcium ions and the hydroxide ions, are coming from, okay? So it's the top equation I want to use to actually figure out things, because that's the equation that has the hydrogen phosphate in it, and that's where my calculation has to start, because that's right now, that's the thing I know. So what I want to do is I want to make an argument about whether I want to find out how much calcium I need to get in there or how much hydroxide I need to get in there. All right. This step is, again, a little bit complicated, but if you think about things logically, I think it should make sense. Okay. So try and bear with me and work your way through the reasoning I'm going to try to use here. In the equation for the actual precipitation, this top equation, I need 5 calciums and only 4 hydroxides, right? So I need more calciums than hydroxides. The calciums and the hydroxides are both coming out of the bottom equation. This one says every time I make a calcium, I make 2 hydroxides. So if I dissolved enough lime to make 5 calcium ions, at the same time, I would get 10 hydroxide ions, right? So what does that tell me? That tells me that I'm always going to have more than enough hydroxides, because they're coming in this 2-to-1 ratio. That says my solution is always going to get twice as many hydroxides as it is calciums, but it actually needs more calciums. So once I get enough calciums, I'll have plenty of hydroxides. Okay, there's going to be excess OH when this whole thing is over, right? So my solution would then be basic, and I could fix that by adding a little bit of acid once I had gotten the phosphates out of there, I suppose. Okay, so what that means is I'm going to calculate how many moles of calcium ions I need to precipitate my hydrogen phosphate. That's going to tell me how many moles of calcium oxide I need, and that'll be a way to answer the problem. So let's do it. This is my whole equation, all right? The thing I know is that my hydrogen phosphates, these are 10 to the 4th liters at 0.0156 molar concentration, all right? So if I multiply those two things together, remember molarity times liters gives me moles, and it's pretty easy here. So that says I have 156 moles of hydrogen phosphate, okay? And that's just 10,000 times that molarity. So that's where I'm going to start my calculation. 156 moles of calcium ions, not calcium ions, wait a minute, of hydrogen phosphate, of HPO4, 2 minus. I need to get to how much calcium I need to get rid of that. So that says my mole ratio is 3 moles of hydrogen phosphate. Requires 5 moles of calcium ions. Okay, so if I stop there, let's actually do this and multiply that part out. This says I need 260 moles of calcium ions. Okay. If I flip back for a second, we can remind ourselves that the calcium ions come here, right? And I get 1 mole of calcium ions for every 1 mole of calcium oxide. So that says the number of moles I need are going to be the same. So if I need 260 moles of calcium ions, that will also tell me that I need 260 moles of calcium oxide. Okay. So again, about the hydroxides, because when I do the dissolving, wrong way, I get 2 hydroxides here for every calcium I make, right? So that says when I get 260 moles of calcium ions, I'm also going to have produced 520 moles of hydroxide. That's going to be way more than I need, because I need, I'm sorry, my pen is not writing anymore for some reason. Let's see if that can be fixed. There we go. Because I'm going to need fewer than the 260. I have twice as many. I have 520, so I have plenty of hydroxide ions, okay? Finally, all I have to do is turn this thing into a mass, which says what? I get 260 moles of calcium oxide times 56 grams per mole. So that's equal to 14,560 grams, it says here, which would be about 14, call it 14.6 kilograms, since my question asked me to find out a number of kilograms. If we calculated we could figure out how much of the hydroxide we used up, right? Because we started with 500 and we had 520 moles of hydroxide ions when we started, right? We're going to use up 4/5 of that 260 moles of calcium. So we could figure out how many moles of hydroxide are left over. If we were actually treating the water, once we got to the point where we had gotten rid of the phosphates, then we'd want to throw in a little bit of something acidic so that we weren't taking all those hydroxides and releasing those back out into the water supply, right? We'd want to neutralize the water before we dumped it back into whatever water system was flowing nearby that this might run into. All right, again, like I said at the beginning, that is definitely not a problem that I would just turn you loose on to do. In fact, one of the reasons I decided to do this as a video instead of in the live class is that I thought it would be hard to break it down into steps that I could even, say, okay, now answer this piece and answer that piece, right? But I still like this problem, number one, because it's a real application. It's kind of at least a little bit of, okay, this is why some people with real jobs in the actual world might need to do some of this stuff, right? Number two is it really does involve all the ideas that we've talked about involving stoichiometric calculations, right? We had to say, okay, it's a stoichiometry problem. We need a balanced equation. We had to think a little bit about ideas kind of related to limiting reactants when I did that deciding whether to figure out from the calciums or from the hydroxides, right? We had the solution part where we had to use our molarity and volume to get moles. So it's all in there in a admittedly slightly complicated format. But I hope that helps kind of tie together a lot of the things we've been doing, right? The class right after this video will be our last day of diving into stoichiometry, and then we're going to move on to chapter 5 and talk about gases.